let's actually put this into practice. Let's take a problem here. Find the local maximum and minimum values of this function. G of x is equal to x plus twice sine of x. And we're only looking between 0 and 2 pi. So step 1, we're going to find all of the critical points. Critical points are x coordinates where the derivative is either 0 or undefined. So the derivative of this function, g prime of x, is equal to 1 plus twice the cosine of x. Okay? When does this derivative equal 0? Well, cosine of x would have to be minus 1/2. There are two values of x that will get us there. If I want cosine of x to be equal to negative 1/2, then a quick check on the unit circle tells us the solutions are 2 pi divided by 3 and 4 pi divided by 3. Okay, so these are our two critical points. Those are the only two critical points, at least in this interval we've chosen for our domain. And once we have those critical points, we are going to test the derivative here. We'll say between 0 and 2 pi divided by 3, take some number out of there that's convenient, plug it into the derivative, I get a positive value. So the original function is increasing on this first interval. Do that again for the middle interval between 2 pi on 3 and 4 pi on 3. The derivative comes back negative. Again, this is a check that we would be doing with a calculator. Then that original function has to be decreasing on that interval. And then the final interval, we check one more time. The derivative is positive here, so the original function is increasing. Well, that tells me exactly what is what in terms of extreme values. So because the derivative changes from positive to negative at 2 pi divided by 3, then we have a local maximum. The x-coordinate is going to be 2 pi on 3. Again, that's exactly where this change is coming from. Change in the first derivative. And the value of that maximum is going to be 3.83, roughly. So this just comes from evaluating the original function at the x-coordinate that we care about. Well, if this one's the maximum, then that other one has to be a minimum, because we go from negative slope to positive slope. So once again, the x-coordinate for that minimum is 4 pi on 3. And I put 4 pi on 3 into the formula for the original function. And that tells me that the value of that minimum is 2.46. Now, can I see this in a picture? Here is the graph of that function. Here are the coordinates 2 pi on 3 and 4 pi on 3 on the x-axis. And I see that, yes, here is a local maximum, and here is a local minimum. Now, they're not the global min and max. They're not the absolute min and max. There's certainly coordinates over here that have larger y values, coordinates down here that have smaller y values. But locally, this point is the highest you can get without having to go down first. This coordinate is the lowest you can get without having to go up first. So you can think of your local minimums and your local maximums. If I was going to have, say, a helium balloon and I let it go and it'll get stuck underneath this maximum of the curve. It can't go up any further without first being dragged over this hump. I would have to pull it down over that hump and then it could try to rise again. It would get stuck right here just of its own accord. Likewise, if I dropped a ball onto this graph, it could get trapped here in this local minimum, this sort of pothole in my function. So if the ball was acting by gravity alone, it would never actually escape this minimum here. I would have to intervene to force it up over that hill, and then it can roll down to some other value. So even though these aren't the absolute extreme values, they would be enough to stop things in this local idea.